This is Dr. Sirisha, working as Associate Professor in Institute of Aeronautical Engineering. Today, our session will be on stacks. What do you mean by a stack? Stack is a linear data structure. Linear data structure which stores the data in contiguous memory locations so that the relation between an element will be to another element only. It is one-to-one cardinality. Stack and queue are two kinds of linear data structures which are prominent in use for the applications of computer, whether it can be an operating system, memory management, in resource management, whatever you take, right? Coming to exclusively about stack, it is the collection of data, homogeneous or heterogeneous, but the structure allows you to either insert an element or delete an element only from one end. The other end is sealed. We cannot touch that, right? So have a look at the picture which I have shown over here. It is an empty stack whose capacity is a max 6 elements. So their index values are given as 0, 1, so on to 5. Top is a variable which refers to pointing the topmost element, that is the most recently inserted element into the stack. Initially, as the stack is empty, it is been initialized with the default value of -1, which gets incremented with each and every value when we push an element into a stack. So stack is also known as last in, first out structure. That means the element which enters the stack last will be the element which is going to come out first. Okay, then let us see this structure which I have shown over here. Here I have inserted 3 elements. So 25, 33, 21. And top is pointing to 21. As I said, top always points to the most recently inserted element into the stack. And we have access rights only to the element pointed by the top. Either we can remove the element which is pointed by the top by decrementing the top so that it will point to 33. Thereby we are eliminating the element 21. Or you can insert an element into the stack which sits on the head of 21 and the top will be incremented, which I am going to show in my further slides. Look at the stack operations. What are all the operations that we can perform on a stack? The basic operation is a push operation, where we are going to add an element to a stack, right? We are going to add an element. Next is pop, to remove an element from a stack, right? Both these operations will be performed on the only end which is open for these operations. We cannot perform either one of the operations from the other end. Other end is totally sealed. The third important operation is peek. Peek is an operation to identify the element which is most recently inserted, or we can, in the other way, we can say that to look at the element which is pointed by the top is nothing but a peek element, right? So these are the two conditions which are further seen, which is one is full and the other is empty. So these two functions are used to check the overflow and underflow conditions of a stack. What do you mean by overflow? First one is overflow. Overflow condition. This is a condition where you are trying to insert an element into an already full stack. So for example, your stack's capacity is 10 elements. Say it is 10 elements. What if you are trying to insert or push 11th element into it? Can it accommodate? Its maximum capacity is 10 elements. As it cannot accommodate the 11th element, overflow condition arises. So is full is a function which is used to check overflow condition, whether overflow condition has occurred or not, right? The next one is empty. Is empty uses underflow condition. This is the next condition. Underflow. So if your top is pointing to -1, what does that mean? In the previous picture I have shown you, it tells you that the stack is empty. What if you try to pop an element from an empty stack? It means there are no elements and still you are trying to remove an element from the stack. In such cases, underflow condition raises and our function is empty is going to depict the same. It is going to check whether underflow condition has raised or not. If underflow condition raises, then it is going to simply say true. If the stack is empty, or else it is going to say yes, there are sufficient elements, we can perform pop operation. It helps in pop operation, whereas isFull helps in push operation, right? Have a look at the basic operations, push and pop, using few pictures. This is an empty stack where top is pointing to -1 initially. Now I want to push 21 into the stack, right? So once I insert 21 into the stack, top is going to get incremented. Top is going to point to index value 0 and the element 21, right? And if we perform peak operation now, we can see that peak is holding a value 21. Peak element is 21, right? Next operation, push 15. Where this element is going to sit? It is going to sit on head of 21, which is 15, right? So 15, now top is again incremented and it is going to point to 15 element, that is to the index value 1. Now the peak element is 15. If I perform push operations using the elements 13, 24, 11 and 15 simultaneously, then this will be the final picture. Have a look at this one. I have inserted 13, 24, 11 and 35, one after the other. So my top is pointing to the topmost element. Now the peak element is 35. What happens if I try to insert 51? Have a look at this picture. Top is pointing to the highest index value, which is 5. That means stack is filled with the 6 elements. Top is pointing to the topmost element or the most recent element, which is on the edge of the size of the stack. If we want to perform a push operation, again, if you want to further insert an element, overflow condition raises. That means a condition which says that the stack is full, it cannot further accommodate one more element, is nothing but overflow condition. In programming point of view, if top is equal to the maximum index, if top is equal to maximum index value, then we can say that overflow condition has reached. When you try to insert an element and this condition is true, then we can say that overflow condition has occurred. Okay, so let's perform few pop operations and understand underflow condition. Pop. When we perform pop operation, we need not mention any element name or value, because by default, whatever the element that is pointed by top will be removed in when we are trying to perform pop operation. So, and we, as I said, we have access rights only to the element which is pointed by the top. Okay, either we can push on the head of it or we can remove it. We cannot touch remaining elements in a stack. So if I perform pop operation, element 35 is removed and top is decremented. Now top is pointing to the element 11, which is right now on top, right? So the peak element is 11 now. What if I perform pop 4 times? So 4 elements are removed. So you can see the element at index 4, 3, 2 and 1 are removed. Thereby the top got decremented. Now top is pointing to 21 at index value 0 and peak value is also 21. What if I perform pop operation now? Means I'm trying to remove the only leftover element in the stack, which is 21. That means the stack becomes empty. What will happen if stack becomes empty? Top comes back to its default value, which is -1. Okay. Now this is the case where the stack is empty. And what if you try to pop once again? That means you are trying to remove an element from an empty stack. When you perform that, underflow condition raises. As you are trying to remove an element from a stack which is empty. So the basic condition which you need to understand for underflow is whenever you write the function for is empty, if the top is equal to -1, then you can simply say that underflow condition raised return without performing any pop operation. If you are writing a function for is empty, then is empty function is going to return true if top is equal to -1. I hope you understood the basic two operations of a stack, which is push and pop. And with that, you understood the two conditions, overflow and underflow, and the peak function, right? So let's have a look at the implementation of stack using linked list. Why linked list we are discussing about? Stacks can be implemented using arrays as well as linked list. There are two options with which we can perform a stack. Okay, so what are the drawbacks when we use arrays to implement a stack? The first and foremost drawback will be we have to prior intimate the size of or the number of elements the stack can accommodate to fix the size of n. Whereas in this, if you are working with linked list, you can dynamically extend the size of the stack by just creating a node. Right? That is the basic advantage of using linked list contrary to arrays. And if, for example, if you have taken a huge size, say 100, array size as 100, and you are limiting your operations to 10 to 15 elements, always the remaining space goes into waste, right? So as you have to be on a safer side, you have taken a huge array for the implementation of a stack, right? The huge space goes into waste. So to overcome that, to optimize the size required, we go for stacks using linked list, right? It works in a dynamic way. We can put whatever constraints we want to and extend the size of the stack at any point of time, right? With the help of a Python piece of code, I'm going to explain you implementation of a stack using linked list. Have a look at this one. The first class, which is class node. This class is used to create a node, right? Whenever an object of this class is created, its constructor gets invoked, thereby two variables get that namespace, which is data and the other is next. Have a look at the picture of a new node, right? Which is having two parts. One is data part and the other is next part. Initially, when we create a node, its next part is going to be none. Actually, next part is meant to store the address of the next node. Okay, store the address of the next node. But when we create a node, it is not having any relation with the remaining nodes because remaining nodes are yet not been created. Once they are created, we can establish a relation between them, right? So initially when we create a node, then its next part will be empty, which in program point of view, we specify it by saying that it is none. Okay. The second class. Here I have named my second class as stack LL, which is relevant to the word stack using linked list. Okay, and its constructor is having two parts. One is start and the other is stop. Why I'm using these two? Start is meant to store the address of the first node. The basic point which you have to understand with the linked list is we need to have the start address to hold the address of the first node. If say 10 elements are there, 10 nodes will be created. We cannot hold the addresses of all the 10 nodes to access them. We can just hold one node's address, so that is the first node's address, so that we can access the remaining. It is a chain reaction, right? So to hold the first node's address, we use start. Okay, and top, as you all know, top is used to hold the topmost, that is the most recently inserted element into the stack. Top is used for that. So this goes with the basic declaration of the things which will be used in the further implementation of stack operations. Let's look at the first operation, which is push operation. To push an element, we need to read the data, right? So using int of input, I'm going to enter the data, which will be stored in the variable data. Next is new node. This is going to invoke the constructor of the class node. Thereby, a node will be created with data part, whatever the data I read, and its next part as none, saying that it is not related to any node yet. It is a node in a nucleic acid which we need to attach. Next, always have a precautionary eye on your code. Cover all the ifs and buts. So I have gone with this code, keeping in mind what if the start pointer, which holds the address of the first node, is empty, which tells you that there is no node or there is no data in the stack itself. Whatever you created just now is the first piece of its kind. Then that's it. To cover that statement, I have used this if clause where I'm going to check if start is equal to none. That means there is no node yet created. Then the new node's address, if the new node's address is say 2000, will be stored in stat. Will be stored in the stat. That means now stat is holding the new node's address. Even top. What is the job of the top? Is to hold the most recently entered element's address. Even that is going to store the new node's address. Okay. So this is the case where your stack is empty. What if your stack is not empty? It is having some value inside. Then the code enters the else part. Have a look. So now we have to insert this new node, that is to push this node onto the top, right? So take a temporary variable temp and store the start address, whatever the address, the first node's address which start is holding, into the temporary, and assign that address into the new node's next part. That is the address part, which is none basically when we created that node, right? Now make that start hold the new node's address. That means you are giving a position. That means you in the start, which was previously holding the address of the first node, as you are inserting a new node into it, now it is the job of the start to hold the new node's address as its starting address. So that's what I have done. So new node's address is stored in stat. Even as the duty of the top is to hold the address of the new node, even new node's address it will be overwritten in the previous content which is stored in the top. Okay, this is how I'm going to perform push operation using linked list for the implementation of a stack. Okay, so I'll show you a few animations on the same. Have a look. With all the address paths, I have mentioned it very clearly, my dears. Please do follow this. Say, here is a start, right, which is holding the address 2000. What is 2000? 2000 is the address of the first node. Okay, so 3000 is the address of the second node. If you try to show repeat the same using arrays, you can show something like this, right? So this is 22, 21, which is located at location 2000, which is located at location 3000, right? And your top is pointing to 21. Okay, so where you have to insert, increment your top, insert the new element 20 here, and now 20 is going to point to the element 20, which is located at location 5000, right? So in terms of arrays, this is the scenario. How we can implement the same using linked list. Let's have a look into it. Okay, so now, as I said, give that temporary name to the first node. This is the first step. Self start is having the address 2000. So whatever the node which is holding a node at location 2000 will get a temporary name as temp. Next. Now the top is being pointed by the first node. Have a look at this one. Now I'm establishing a relation. Temp. What do you mean by temp? 2000. Where you are going to enter it in a new node next part. I'm specifying it as next part. So where is it? Here it is. That's why I have colored it as red, my dears. Whatever the little bit changes that we are going to do, I'm going to mention it in a different color. Okay. So 2000. Now new node is saying that its next node is at location 2000. This is your new node. Okay, then what else you have to do? You have established a relation between new node and temporary. Temporary is nothing but your previous first, right? On its head now 20 is going to come and sit. Then next our agenda is to change the content in the stat. Stat is a pointer variable which holds the address of the first node. Now 21 is no longer the topmost element, 20. So what we have to do? We have to override the content 2000 with 5000. That is, have a look at this one. New node which represents 5000 is going to override the content in self stat which is 2000. So this is the change. Now have a look at this picture. Started saying that the first element is at location 5000. And the node at 5000 is saying that next element is at 2000. When you go to the location 2000, it is saying that my next element is at 3000. Can you see the chain? Now we have performed a push operation. Right? We have successfully completed the push operation. Only thing is read a node, read the first of all data part, create a node with that data, right? Then establish a check first of all, is the self start none or not? If it is none, store the address of new node into the stat so that you are creating the first of its kind node. If the stat is, that is the self stat is not empty, that means a stack is already existing, then name the first node of the stack as temporary, store its address in the new node next part, and override the content of stat with the new node's address. Thereby, we are changing the relation, right? Or we are performing the push operation. Okay. Let's have a look at the second operation, which is pop operation. Pop operation is nothing but deletion operation, right? So, first of all, name the pop. We are trying to remove the first element from the stack, right? As we are trying to remove the first element from the stack. So, I'm going to give a temporary name to the stack, right? I'm supposed to remove that. That is the main agenda. So my preliminary step, what if my self start is none? Or I can even write it as, in the push operation I have used this one. What if self start is equal to none? Which tells you that the stack is empty. What did I tell you? How can you remove an element from an empty stack? We cannot do that, right? So I'm simply going to say underflow condition, print underflow and return, thereby specifying that pop operation cannot be performed. The same point I have not used in case of overflow condition. I have not checked in case of push. Why? Because as linked list dynamically create the nodes. They dynamically create the nodes. So there will not be any issue of overflow condition. If the size of the stack, if you are saying that you have started with 5, you can extend it to 6, 10, 20, 100. You can extend it dynamically. You are going to create a node, push a node into the stack, and thereby increase the length. You will not encounter the condition of overflow. Whereas always there is a chance of encountering the case of underflow. Even if your start or the top are having the content none, saying that no node is present, and how you are going to delete a node, right? So underflow condition may rise. So I have checked the underflow condition here, and if that encounters, I'm going to simply read. I'm going to come back. Okay. Next, what if the top is not none? Elements are existing. Then, if else if there is a condition, if a case where temporary next is equal to none, means whatever the first node that is the last element. When guys have a look at this one and understand when will this condition raise. For example, say your start is something like this, which is holding a location 2000. Mane, your node is at location 2000 and data part is 20. This is the one whose name is temp, and its next part is none. This is the condition they are talking about. That means you have named the first node as temp and its next part is none. What do you mean by that? It means that it is the last node or the only node that is present in the stack. Means if we remove that, what happens? The stack becomes empty, right? So that's what we have explicitly taken it as a special case, a case where you are going to remove the only element left in the stack. So what should be the content in the start and top? Once you remove the only element in the stack, they both must come to their default values, which is none. Okay, that's why I have explicitly taken this as a case. I hope you understood these two cases, these two explicit cases. Right? Right. Now, a normal case, a case where the else part goes with a case where the node which you are trying to remove is not the last element or the only element in the stack, and the stack is not empty. You are having a handful of elements in your stack. What will happen if you remove the first element from it? Let's have a look at this piece of code. Understand, guys. First of all, name the first node as temporary. Okay. Then, with the next part of temporary, that is the second element, is going to be the new start, right? So name it as the new start, and the address of the new start, place it in the start. That is, the start is the one which holds the address of the first node. So the second node is the new start now. So it is now start is going to hold the second node's address. Now free or empty the first node. Delete it. I'll show you guys, don't worry. Look at this one. A case where I'm having two elements, 21 and 22. If I do this using arrays, implement this. So 22, which is at location 3000, 21 is at location 2000. My top is pointing to 21. What if I perform a pop operation? If I perform a pop operation on this one, top gets decremented. Now it is going to point to 22, which is at location 31. That means I have removed 21, right? So how to perform the same using linked list is the task, right? So have a look at the piece of code which I'm going to show you through some few animations. First of all, I'm going to name the first node as temporary and the second element as new start. Because as I've shown you, if I remove the top element, the new top element will be 22. Am I right? So how to specify the say temp next? It's very simple. New start is equal to temp next. What is temp next? 3000. Place it in new start. That is the node at location 3000 will get a new name as new start. Okay. Now, as you see, you get the new name as new start. Right? Next, what we have to do? We have to, the only thing, if you want to remove the first node temporary, where is it linked to? Very simple. The start is the key. He is holding the address of the first node. You overwrite with the address of the first node. That's what I have done. New start is having an address 3000, right? I have placed in start. So I have overwritten the content 2000 with 3000. Now have a look at this. Key look at the second picture. Start is pointing to a location 3000. Thereby you have come to the new start. Right? So simply now you can see that temporary lost the previous relations which it had with the elements. So simply delete temp and you are going to free the memory allocated for the first node, right? Now have a look at this one. What will be the ultimatum? Start is holding an address 3000 and at location 3000 you have a node 22 whose next part is none and which is a new start, right? It is going to point to this node, right? So this is how you are going to perform pop operation. Yes, please remember, in case of pop operation, we have three cases. A case where the stack is empty, that is underflow condition raises. Second is a case where the stack is holding only one element, that is the last or leftover element in the stack. If you try to remove it, what will happen? It happens is the start and top will get the default initial values, which is none. And the third case is where the stack is having handful of elements. Okay, I hope you are able to understand the basic two operation push and pop of a stack. So what are the advantages of using a stack? So stack has many advantages, like it is able to hold multiple data types, right? It is not a homogeneous data structure, something like that, heterogeneous. It is many kind you can use. It is they're both flexible and fast, right? If you implement with using the linked list, it is fast. But every advantage will have a hidden disadvantage. That is, so every linked list suffers with the space complexity because every node holds the address of the other node, and the memory which is used to store the other node is high if the number of nodes raise in a linked list, in a single linked list, right? So that itself becomes the biggest disadvantage. Okay. Potentially, queues can be infinite length compared with the use of fixed length arrays. As I said, even stacks also have this advantage. Stacks can be extended to infinite length, as I have previously explained. The basic disadvantage of using a stack. So when can we say that your stack is full? It is when it is pointing to the last element, right? But in case when you implement it with using linked list, you will not find that. So disadvantage will not be there. Guys, the beauty of a stack is it does not allow its any one of its operations from the other end. That is the basic beauty. And you might feel that if you are restricting the operations from the other end, what is the fun of having it, right? So the basic advantage is at few spaces, it is required to stop the access from the other side to put a restriction. It is stack is a style or a design structure, design pattern which is meant to store the data if it is required to store like that only. For example, look at the applications of a stack. Evaluation of an arithmetic expression, right? What do you mean by evaluation of arithmetic expression? Humans understand infix expression. Am I right? We understand if someone writes A plus B, you will understand. Do you guys understand if somebody writes A, B plus, do you understand this one? If I tell you add 5, 3 plus, will you understand? It goes bouncer from your head, right? Which is known as postfix expression, where the operators are going to follow the operands. You are going to write the operands first, then the operators, because the system understands postfix expressions only. So if you want to evaluate an expression, you have to convert that into postfix. That is stage one, step one, you can say. Once you get postfix expression, evaluate this postfix expression. This is your step two. And both these steps need stacks for its implementation. Right? We push the operands and operators into the stack and we perform these two steps, infix to postfix and evaluation of postfix. Internally, our arithmetic logic unit uses stacks for evaluation. Okay, so see, we feel that A plus B is a simple operation. Anybody can do it, yes, but large operations, right? If it is an expression which is having 20 to 25 operands followed by brackets and all, how we are going to evaluate it? For example, let me take 5 by 3 multiplied by 6 by 2 exponent of 4 plus 3 multiplied by 2 power 6 minus 81, something like this. Right? So if I put nested brackets, if I further want to extend the complexity, what if I extend this in this way, using inner brackets? So what the system is going to do is, it is going to, this is an infix expression, right? It is going to take a stack. Using the stack, it is going to convert this infix to postfix first. The main advantage with postfix expression is it is free of brackets. Once you convert infix to postfix, it will no longer have the brackets in the concern. So, and that postfix expression, that your system calls as intermediate result, using another stack, it is going to evaluate it and give you the result in fraction of seconds. I have given a very tiny expression, but systems, when they use data of a huge terabytes, it becomes a complex expression. Right? Not only these arithmetic expressions I have used, so you might be having bitwise expressions, logical expressions, relational, many expressions, right? Many operators you can use in a single expression. For that, stacks are useful. Next one, backtracking. Backtracking is an operation which is used by your OS to keep track on the things that are happening. That is the request, the the resources, the extra resources, asking the operating system to help, right? For example, to the operating system, they might be having a scanner asking for it, an operator like an external hard disk request. So many resource requests will be there. To track them, stacks will be used. Next is delimiter checking. It is also known as parenthesis balancing. I hope you know what parenthesis balancing is, right? So every open bracket must be closed, right? So the people who are familiar with C programming, C++ programming, Java, they are used to this one. So whenever you forget to close a flower bracket, immediately the compiler is going to raise an exception saying that you have forgotten a bracket, you have misplaced one. Or if you put an extra bracket, it will say misplaced, right? So how the system is going to do, it is going to do with the help of stacks. That is nothing but delimiter checking or parenthesis balancing, right? Next one is reverse data. If you want to reverse the data, stacks are the best one. Push the data as it is into the stack and remove, pop one by one character and print it. That itself will give you the reverse of data. That is very simple. Next is processing of function calls. When we call a function, then the controller will abruptly break its control from the execution and take you to the function definition called, right? Function definition. Once the function definition gets executed, the function call over, where the control must return to. That is the primary question. So all the function calls will store its return address first before leaving its place. So these written addresses are held by stacks. They help you to store the written addresses. So whenever a function call is end, the control will approach a stack which is storing the addresses, will fetch the address from it, and wherever the location it shows, it will go to that location and get back to the track in the main function, right? So it can be a recursive function, normal function call, any function call, right? So for processing of function calls, stacks are used, extensively used. As I said, there is no comparison between queues and stack. No one can bet that stack is having this advantage whereas queue is having this advantage. No, both these data structures are being designed for their own purpose. This means stacks are meant and used for the purpose where access of only one side is required, and the other side you should not give permission to access the data, even just to read also. Only the topmost content must have the privilege to show its face, remaining should be in hidden state, right? Yes, as I have shown the 5 applications of stack, these 5 applications pose or restrict the application saying that only the topmost content will be shown, remaining will not be even shown, right? So that is the purpose of a stack. Whereas queues are cases where you want to have a privilege that the push and pop operations cannot be done at the same end, and they have to be done at two opposite ends, right? Just like insertion at the rear and deletion at the front, right? So yes, we do encounter such cases. In those cases only, we use queues. So these two data structures are designed for their own benefits and usage. So we cannot comment on the advantages of stacks on queues or queues on stacks. Both are versatile data structures. Guys, I hope you understood what a stack is. What are the basic operations that we can perform on a stack, which is push, pop, peek, is empty, and is full, with where is empty and is full are going to rely on underflow and overflow conditions respectively. Then we have seen the stack operations implementation using linked lists. We have seen the advantages and disadvantages of stack and the applications of stack, right? So this is the full story about stacks. And in my next video, I'm going to explain you the working of queues using linked list, the basic operations that are performed on queues, then their implementation using the linked list with the pieces of animation, followed by advantages and disadvantages of linear queues, followed by the applications of queues. I hope you understood this session. Please do comment on the same. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.